This is going to be your Unit 8 Day 2 lesson. In this lesson, we're going to be focusing on the applications of exponential functions. So if you think back to what we did last lesson, that was on exponential growth and decay. And today we're just going to be doing tons of different application problems. So first, your warm-up is to start thinking about one of those applications, which is interest. So what is interest? How can you earn it? And does compounding interest more often give you unlimited returns? Okay, let's see. So number one, your first question is to decide which of the following investments would give you more for your dollar. So you have $1 to invest. Which option is better? So A, invest $1 at an annual interest rate of 100% for 1 year. So at the end of your first year, you've gotten 100% back, so therefore you end the year with $2. Whereas B, we're investing $1 at a semi-annual interest rate of 50% for 1 year. What that means is that you're investing twice. So half the year goes by and you have the interest rate of 50%, and then the other half passes and you get 50% more again. So here's a way that we would represent that. This first bit is 1 plus 0.5. The reason why is we start with that $1, and then since our interest rate is 0.5, we add on 50 cents. Okay, so we have $1.50 halfway through the year. And then we add on to that, we add on 50% of the 1.5, because that's what we're going to get for the second half of the year. Okay, so this is our first half, how much we would have, $1.50, and then this is the second half, we would gain another half of 1.5, so we would end the year with 2.25. So that shows us that indeed option B is going to be the better option. Okay, so we compounded semi-annually more often and got more money. Number two, we're going to go through this table, which is going to help us to see whether compounding interest more often, so having the interest rate more, can give you $1 million for your dollar over a year. Is that possible? Okay, let's go ahead and see. So we're going to start with the annual. What if I compound annually? Then that means that my N is 1, the number of times that the interest is calculated. The formula that we use is in this column right here, 1 plus 1 over N, all to the nth power. So if N is 1, then we're taking 1 plus 1 over 1 to the 1, and we get $2, right? We just get that $1. That's exactly what we did up here with 1A. Semi-annual, that's what we did with B, and we found that we got $2.25. When it's 4, so we're taking 1 plus 1 over 4 to the 4th power, we end up with 2.44, so $2.44. All right, so let's keep moving on. So monthly, how many times would I be calculating my interest? Well, since there are 12 months in a year, my N is 12. So our equation would be 1 plus 1 over 12 to the nth power. Right. And when we actually calculate that out, we would end with $2.61. Okay, what about weekly? If we did it weekly, our N, the number of times we're calculating interest in a year, we have 52 weeks in a year, so therefore we use 52 as N. We plug that into our equation, our formula, and we get $2.69. So we're just taking 1 plus 1 over 52 raised to the, even though this is an N, it should be more specifically 52. Okay, if we compounded daily, we'd have 365 days. We would go ahead and plug that in, and we would get our result, $2.71. So we're increasing little by little. Okay, what if we did it hourly? So every hour, more interest is calculated. Well, we have 8,760 hours in a year. Plug that in, and we get $2.72. Okay, what happens when we compound every minute? We plug in our equation. Oops, I forgot the little N there. 272 again. Okay, look at what's happening. So the more often that we calculated our interest, the more often that we compounded our interest, what happens? So that dollar that we invested, what happened was it approaches $2.72 at the end of that dollar. We can't really compound any more than that second, so it looks like it's going to go up to that $2.72. That's the maximum that we can have. Okay. So, I want you to use your calculator and plug in e to the 1 power. I'll show you on your calculator where that is. Oh, looks like my calculator won't work actually. But on your calculator, you can actually plug in e. On the left-hand side, near the bottom, you can find the button for e, and it's e to the x, and you can just plug in e to the 1st power. And what do you get for that? You should get e is equal to 2.72, which is the same value that we just found. Okay. What if you were to graph the function y equals e to the x? Go ahead and try to graph that and sketch it below. So pause the video and try to sketch that. Now the question is, what type of function is y equals e to the x? Well, if you think back to last lesson, it would be an exponential growth function. We have our base to some exponent x. Okay, now we're going to dive into thinking more about this compound interest, and one way to do it is there's going to be a lot of vocab here, okay, so a lot to learn about what exactly does it mean to compound interest, right? Fun quote here, Albert Einstein, he said that compounding interest is the greatest mathematical discovery of all time. What? That is a big claim, so let's go ahead and see why he said that. So, to start with, there's some good. Okay, compounding is a way to get rich slowly, is what you can say. So compound interest, it makes your savings grow. The more you save, the more it grows. The longer you save, the more it grows too, and the higher the rate, the more it grows. Okay, so for example, I can say I want to put aside this much money, and if there's compound interest, it's going to grow that money over time, okay? The higher my rate, the more money that I will get. Annuity is another term, is saving a set amount of money regularly. For example, saving $100 per month every month. This is an excellent way to become very, very rich, especially if you have good interest, okay? So this lesson maybe can teach you how to get some more money. Okay. But on the other hand, there's some bad stuff about compound interest. So think about loans and mortgages. So mortgages is what you take out to pay for a house, okay? Eventually one day you may take out a mortgage. College loans, right? Other loans that you might take out as well. So with loans and mortgages, you're borrowing other people's money. You're using others. And so you're paying them in order to borrow that money. So the more you borrow, the more you pay. The longer you borrow, the more you pay. There's an interest on loans and mortgages. And we come to the ugly. So compound interest can also make your debt grow. So if you're not paying off at least the interest added each month, you could keep paying your debt forever and never pay it off because you just keep accruing more and more and more and more interest, especially if you're not paying it off, right? So basically, interest is just going to keep growing and growing. And if that's growing not from savings but from debt, then you're just gonna, for money that you owe, then you're just gonna keep owing more and more money. So this is just a little bit of background, okay? So even though interest is expressed as an annual percent, usually the interest is compounded or paid to you more than once a year, okay? So interest, you'll get a 24% APR, which is annual per year, something like that. But usually it's compounded more than once, okay? So for compound interest, there are two different equations that we're going to use. So both of these are going to be important. Our first one, A equals P times the quantity 1 plus R over N to the NT. And here we have all of our variables labeled. So A is the final amount. That's oftentimes what you'll be calculating. P is your initial amount. T is the time over which you're gaining this interest. R is the rate. And N is the number of times compound. For example, if you are compounding it semi-annually, your N would be 2. So you plug in an N in 2 for N. Over here, A equals P times E to the RT, so that E is that 2.72 number, right? You'll use your calculator and actually plug in E. This is for if we compound continuously. So I'll go ahead and write that in. So compounded, or here, continuously. Okay, so we're going to use this equation if it says the interest is being compounded continuously. So again, same variables, but they look a little bit different, okay? Alright, so let's go ahead and start to apply these. Alright, so how your savings can grow. Here's your simplest case. So you have a one-time investment that is compounded annually. Frick and Frack are co-workers. Frick is 20 years old and Frack is 30. They both receive a special year-end bonus check for $20,000. Frick tells Frack that $20,000 is a perfect retirement nest egg, and he invests it at 10%. So Frack does exactly the same thing. Neither of them ever adds anything to this investment, so they just take that $20,000 and they invest it at 10% annually. If they both retire at age 65, how much does each have for retirement? So what we are going to be using for this one is we're going to be using this equation down here. A equals P times 1 plus R over N to the NT. So we have, let's start off by trying to come up with the equations that we're going to use. So Frick, we have A. A is equal to the initial value. So 20,000 is our initial value times the quantity 1 plus, do you remember what it is? It's going to be R over N. So R is the rate, and if we look here is our 10%, that's where we got the 0.10, and the N is 1. Okay, so that was how many times we compound it over the year. So we only did it once. And then we raised that to the NT. Okay, so I have a 45 written down here. That's because Frick is 20, and he's going until he's 65. So that means it's 45 years, so T is equal to 45. Okay, Frack, on the other hand, or well, I guess then we would solve it, right? Oh, look at that. So Frick's $20,000 turned into almost $1.5 million in 45 years. Whoa. Frack, on the other hand, so he starts with his A. He has the same initial, right? And he has the same interest, but what changed is the years. Instead of a 45, he has a 35. And what you can do now is plug this into your calculator and calculate, and you would get $562,048. Look at that difference. Isn't that crazy? Almost $1 million difference because Frick started investing 10 years earlier. So I know it might not sound convincing now, but when you get to your first job, you're going to be told, start investing. Well, here's the evidence of why you should start investing. Look at that difference. So, as you're thinking about this, right, think about how much is that difference, what makes this difference, and what does this tell you about the nature of compound interest, okay? Alright, we're going to do one more example in this video, and then we'll move on to the second video. So example 2, now instead of investing your bonus check, you decide early in life that you want to save some money. So you deposit $1,000 into an account that pays 8% annual interest. Find the balance after 2 years if the interest is compounded with the given frequency. So let's say your interest is compounded annually. So we first start by writing the equation. So we have A, our final amount, is equal to our initial value, which is that $1,000, times what? Times the quantity 1 plus R over N, which R is that 8%, so it's 0.08, and annually means we're only doing it once per year. And I square that because I'm doing it after 2 years. Okay, so it's 2 times 1, N. And I find that number, $1,166.40. Okay, what if it's quarterly? What would change? Well, our initial value is still the same. We have 1 plus now 0.08 over 4 because I'm investing it 4 times a year, raised to the 2 times 4 because I still have the 2 years, but 4 times a year. And I have that number as well. And then daily. So one more change to get daily. So A is equal to 1,000, our initial amount, times 1 plus what it's going to be, 0.08 over 365, because there are 365 days a year, raised to the 365 times 2. And that's equal to $1,173,000, $1,173.51. Alright, so this is all we got through for this video. Go ahead and watch the next one for the rest of the examples.